Hey there, and welcome to the Explainer. Today, we're moving beyond just the steepness of a curve. We're going to dive into the calculus that uncovers its hidden story, the very way it bends and shapes itself.
So think about this. We all know that slope tells us how steep a curve is. But what about its bend? I mean, we can see the shape of a graph, right? And we know the first derivative tells us how steep it is. But how do we actually, mathematically describe its curvature? How do we put a number on whether it's bending up, kind of like a bowl, or bending down, like a hill? Well, to answer that, we've got to look beyond just the first derivative. We need something more powerful, a tool that can tell the whole story of the curve's bend, or as mathematicians like to call it, its concavity. And that tool? It's the second derivative. And honestly, it's pretty much exactly what it sounds like. You take the derivative of the derivative. So we start with our function, we find its slope, and then we just find the derivative of that slope function. Okay, so what does this actually tell us? Well, it measures how the slope itself is changing. Is that slope getting steeper? Is it leveling out? Is it maybe flipping from negative to positive? The second derivative, well, that's where all the answers are. And here's where it gets really cool. We can use this whole idea to literally read the bend in the curve, that property we call concavity. And the secret? It's all in the sign. Yep, just whether that second derivative is positive or negative. So let's break it down. There are two types of concavity. First, when the second derivative is positive, we say the curve is concave up. You can think of it like this. Its slope is always increasing. And if you drew tangent lines, they'd all sit right below the curve. On the flip side, when the second derivative is negative, the curve is concave down. Now, its slope is decreasing, and those tangent lines, they sit right on top of the curve. Here's a really simple way to remember this, and it comes from some material out of the University of Sydney. A concave up curve. Well, it's shaped like a cup. You can literally imagine it holding water. And you guessed it, a concave down curve is the exact opposite. It's shaped more like a mound or maybe a frown. It definitely can't hold any water. It's a super simple visual, but man, is it effective for remembering the difference. Okay, so if a curve can bend up and it can bend down, it just makes sense that it could, change from one to the other, right? So what do we call that exact point where the big switch happens? That special spot is called a point of inflection. And for a point to get this fancy title, it has to meet two super strict conditions. First, the second derivative has to be 0 right there. And second, this is key, the concavity has to actually change. So, and this is really the most important part, it is not enough for the second derivative to just be 0. That only tells you that you've got a potential candidate. You have to prove that the curve's bend actually flips, from up to down or down to up, right at that specific spot. Okay, so let's just recap the key identifiers. An inflection point is where the curvature changes. Condition 1, the second derivative is 0. Condition 2, and this is the big one, the concavity changes from one side to the other. Oh, and there's also a special case to keep an eye out for, a horizontal point of inflection. That's where the curve also just happens to be perfectly flat at that same moment. All right, theory is one thing, but let's see how this stuff actually works in practice. We're going to put these tools to the test and go on a hunt for a hidden turning point in a real function. And for our case study, we'll use the function y equals x cubed plus x. This is a really great example because, honestly, its story isn't obvious just by looking at the equation. Now, the process for finding an inflection point is it's super logical. It follows these 4 steps. First, find the first derivative. Then, find the second derivative. Next, set that second derivative to 0 and solve for x. And finally, the most important step, you have to test for a change in concavity around that x value. So for our function, y equals x cubed plus x, once we take the derivative twice, we find that the second derivative simplifies down really nicely to just 6x. Okay, step 3. We set that second derivative equal to 0. So 6x equals 0, and yeah, the solution here is pretty straightforward. X has to be 0. Now remember, this just gives us our candidate for the point of inflection. And now for the final crucial test. We've got to check the sign of our second derivative on either side of x equals 0. So let's try plugging a negative number into y double prime equals 6x. Say -1. Well, we get a negative result, which means the curve is concave down there. Now let's try a positive number, like +1. We get a positive result, which means the curve is concave up. So because the concavity changes, it goes from down
to up as we pass through x equals 0, we have officially met both conditions. We have confirmed it. There is a true inflection point right there.
And there you have it. You now have the tools to read the hidden story of a curved shape. Think of the second derivative as kind of a secret decoder for graphs. It lets you see past just the steepness and really understand the story of a function's shape. And this isn't just about abstract curves on a page. It tells us exactly where a system's behavior fundamentally changes.
So, you can now read the story of a curve's bend. But that's just one of the amazing stories hidden in the language of calculus. It really makes you wonder, right? What other stories are out there just waiting to be discovered?